And you may think that anesthetics work by sending you into some deep sleep or by blocking your receptors so that you don't feel pain. But in fact, most anesthetics don't work that way. What they do is they introduce a noise into the brain so that the neurons cannot understand each other. They're confused. And you cannot make a decision. So while you're trying to make up your mind what the doctor, the surgeon is doing while he's hacking away at your body, he's long gone. He's at home having tea. So it took the universe 11 billion years to build a brain. It had to improve it a little bit. It had to add to the frontal part so that you would have instincts because they had to cope on land. But the real big step was the ultimate solution today of the universe as we know it. It's the pinnacle, it's the final product that the universe has produced to perform more complex functions. So you can think of the neocortex actually as a massive grand piano, million-key grand piano. Each of these neocortical columns would produce a note. You stimulate it, it produces a symphony. But it's not just a symphony of perception. It's a symphony of your universe, your reality. So the holy grail for neuroscience is really to understand the design of the neocortical column. And it's not just for neuroscience, it's perhaps to understand perception, to understand reality, and perhaps to even also understand physical reality. So what we did was, for the past 15 years, was to dissect out the neocortex systematically. It's a bit like going and cataloging a piece of the rainforest. How many trees does it have? What shapes are the trees? How many of each type of tree do you have? Where are they positioned? But it's a bit more than cataloging because you actually have to describe and discover all the rules of communication, the rules of connectivity, because the neurons don't just like to connect with any neuron. They choose very carefully who they connect with. It's also more than cataloging because you actually have to build three-dimensional digital models of them. And we did that for tens of thousands of neurons, built digital models of all the different types of neurons we came across. And once you have that, you can actually begin to build the neocortical column. And here we're calling them up. But as you do this, what you see is that the branches intersect actually in millions of locations. And at each of these intersections, they can form a synapse. And a synapse is a chemical location where they can communicate with each other. And these synapses together form the network or the circuit of the brain. Now, the circuit you could also think of as the fabric of the brain. The reason is because the most important design secret of the brain is diversity. Every neuron is different. It's the same in the forest. Every pine tree is different. You may have many different types of trees, but every pine tree is different. And in the brain, it's the same. So there's no neuron in my brain that's the same as another, and there's no neuron in my brain that's the same as in yours. And your neurons are not going to be oriented and positioned in exactly the same way, and you may have more or less neurons. So it's very unlikely that you got the same fabric, the same circuitry. So how could we possibly create a reality that we can even understand each other? Well, we don't have to speculate. We can look at all 10 million synapses now. We can look at the fabric. And we can change neurons. We can use different neurons with different variations. We can position them in different places, orient them in different places. We can use less or more of them. And when we do that, what we discovered is that the circuitry does change. But the pattern of how the circuitry is designed does not. So the fabric of the brain, even though your brain may be smaller, bigger, it may have different types of neurons, different morphologies of neurons, we actually do share the same fabric. And we think this is species specific, which means that that could explain why we can't communicate across species. So let's switch it on. But to do it, what you have to do is you have to make this come alive. We make it come alive with equations, a lot of mathematics. And in fact, the equations that make neurons into electrical generators were discovered by two Cambridge Nobel laureates. So we have the mathematics to make neurons come alive. We also have the mathematics to describe how neurons collect information and how they create a little lightning bolt. So there literally are only a handful of equations that you need to simulate the activity of the neocortex. But what you do need is a very big computer, and in fact you need one laptop to do all the calculations just for one neuron. So you need 10,000 laptops. So where do? You go to IBM, and you get a supercomputer because they know how to take 10,000 laptops and put it into the size of a refrigerator. So now we have this Blue Gene supercomputer. We can load up all the neurons, each one onto its processor, and fire it up and see what happens. Take the magic carpet for a ride. Here we activate it, and this gives the first glimpse of what is happening in your brain when there's a stimulation. It's the first view. Now, when you look at that the first time, you think, my God, how is reality coming out of that? But in fact, you can start, even though we haven't trained this neocortical column to create a specific reality, but we can ask, where is the rose? We can ask, where is it inside? If we stimulate it with a picture, where is it inside the neocortex? Ultimately, it's got to be there if we stimulated it with it. So the way that we can look at that is to ignore the neurons, ignore the synapses, and look just at the raw electrical activity, because that's what it's creating. It's creating electrical patterns. So when we did this, we indeed, for the first time, saw these ghostly-like structures, electrical objects appearing within the neocortical column. And it's these electrical objects that are holding all the information about whatever stimulated it. And then when we zoomed into this, it's like a veritable universe.